Thank you, everybody, for joining us tonight for our prime time AMS Weather Band webinar, with the title of our webinar being Weather Forecasting Model Performance, What Everybody Should Know. And as our attendees start trickling in here at the top of the hour, I just want to take a few moments and just say, I think all of us have that heavy heart today after the events yesterday and the events last week. It's tough on my family. We've got 5 kids, and I think everybody has had some reflection today. And if anything, I think one of the feelings that people have is feeling a little bit powerless. But I want to transition that into what a lot of people are sort of doubling down on and really thinking about today is the weather, water, and climate enterprise mission of public safety, and that we aren't powerless. We all have an ability to keep family members, loved ones, our community safe from extreme weather, and among other things. And we all have our part, whether you're a professional, whether you're an amateur, whether you just love the weather and you've joined the weather band to get exposed to our larger community. There's a lot that you can do. You can, you don't have to be a professional to make a difference, make an impact in your community. And even the topic tonight on model performance, models are at the heart of the weather, water, and climate enterprise. The heart of the weather forecast really, starts with observations and then goes right into our supercomputers and the model output. And so we have 2 experts tonight, Dr. Neil Jacobs, who is currently the Chief Science Advisor for the Unified Forecast System, which is a part of the University Corporation for Atmospheric Research. Neil was the former acting NOAA administrator, and before that was with Panasonic Avionics, and he is a fellow North Carolina State University graduate, along with myself. And we also have Dr. Alicia Bentley, who is an atmospheric scientist who specializes in evaluating weather models at NCEP's Environmental Modeling Center. So thank you, Alicia, and your educational roots are at SUNY University of Albany. And just a little background, I guess I didn't even introduce myself. My name is Doug Hildebrand. I work for the National Weather Service at headquarters and am the preparedness and resilience lead, and sort of carry the flag of the Weather Ready Nation program. And I'm also the chair of the Weather Band committee here. And part of our duties as this committee is bringing guests like Alicia and Neil into the fold. We're going to have a very conversational hour here in this webinar. And for those joining us, you can send a question, send a comment in the Q&A function at the bottom of your computer screen there. And, we'll try to get to everybody's questions. This is being recorded, so if there are issues on your end about participating in a recorded session, you can drop off. You can actually, watch the recording later. But it's awesome. We have so many topics to cover. I know Neil and Alicia, as we were prepping for this, it's like, oh my goodness, what can we all get in an hour? So I will sort of dive in head first, Neil, with the title of our webinar ends with what everyone should know. So what are a few headlines that everybody, whether you are, working at EMC or you are just a lover of weather, what does everyone need to know about models and model performance?
Well, first of all, thanks for that introduction, and thanks for inviting me. It's a thrill and an honor to be here with you and Alicia and talking about NWP. What everyone should know is it is mathematically impossible to get a perfect forecast. That's rule number 1. It's in general, NWP is an initial value problem. So you're using a set of mathematical equations to take your best guess at the current state of the atmosphere and then predict the future going forward. So it's a whole complex web of nonlinear processes and assumptions and approximations, and everything is chaotic in nature. And so it's only going to degrade as you go further out into the future. And if that's not scary enough, even if the physics equations were theoretically perfect and all your assumptions were theoretically perfect, you're still subject to how well you observe the atmosphere. And those observations have varying levels of sensitivity and accuracy. And even if those were perfect, there's something called representativeness error, which is basically just the reality that that observation is really only valid for a few centimeters around it. And when you're running a model at a grid spacing of kilometers to tens of kilometers, you're already extrapolating reality. So to me, it is exciting and fascinating. It's amazing that we can take what limited information we actually have and even come remotely close to predicting the future. There's really not a lot of other areas in science that can do things like that. So that's what drove me to this field, really.
Great. So that's one, take home, and it's an important point, because at times we feel like, whatever the model output gives us is the forecast and is going to be reality, because it can be so almost lifelike in, really projecting how the atmosphere evolves. Alicia, thoughts on that comment? And, I guess I would also pass on that question of, like, what do you think everyone should know?
Well, I'll do both at the same time, because you set me up with a meatball on that. And it's for students maybe, but also forecasters. They're very well aware of this too. But like you said, forecasts are getting so good, especially these deterministic forecasts look so good and so real that it seems extremely likely when you're looking at a day 16 forecast, like this is a solution, like this is going to happen. And what I would tell people is ensembles and probabilistic forecasting is, where we're going now. We're going there in global models, we're going there in regional models, convective allowing model scale. And it buys you skill. I mean, to look at an ensemble of predictive solutions and to take potentially the mean of that, look at the spread of that, you can increase by 2 days at the global scale right now your useful period of skill by looking at an ensemble versus a deterministic model. So if I had to, pound down the door and say a thing that I firmly believe in is to utilize ensembles whenever possible, because it tells you more about the forecast than maybe that one deterministic model can tell you.
That's a great point. We should come back to ensembles and discuss the proper use, but I've got a story about deterministic high-res models. So I was at a meeting, it was an AMS meeting, and I know it was after Katrina because the simulation was of Katrina. It was very high resolution landfall. I think it was run at like 500 meters or 1 kilometer. And I remember someone in the back, and I don't know who it was, raised their hand, and they were like, those are some pretty, great looking rain bands. How do you know all those storms are in the right place? And it was like the longest period of awkward silence because they don't, just because the forecast is high res and it looks really cool doesn't mean it's actually correct.
That's right. And so you almost, the expectation of that accuracy, is almost working against that.
It is. It's a little bit misleading because people think, oh, if it's 1 kilometer, then this is going to be accurate to the end of my block or whatever. And that's not, I mean, Alicia's the expert on this. I should be asking you this, but I've seen a lot of situations where you take a high res run and you regrid it to a lower res and your verification on QPF actually improves.
Right. No, it happens all the time. I mean, it's very interesting. We're moving our verification to, some higher resolution grids going forward, and lower resolutions can actually improve your skill score depending on what you're looking at. So yeah, resolution matters. It all it's all relevant. And I think it's important to recognize that, how do I say this? Just because something's pretty, like, it doesn't make it accurate. Like it, just because it's like a beautiful looking map, like, doesn't mean that it's any more reliable or accurate than another. So, yeah.
So Neil, you know, especially I think for those who may not be playing, you know, numerical weather prediction inside baseball, give us a, you know, sort of a quick and dirty, almost like a history of global weather models. Obviously, you know, people may, if they watch morning television, they may see the, you know, American model pitted against the European model. And, you know, oftentimes they'll have different solutions, and it's like, you have to, you know, which one's going to come out on top. And then even, you know, model skill improvements over the decades. I mean, we really have entered, I'd say, you know, I've been in the Weather Service 20 years, and in those 20 years, you know, an incredible advancement, even over the last 5 or 10 years. You know, obviously supercomputers are getting more and more powerful. So kind of just lay it out, you know, since the history of the dinosaurs.
Well, so let me start with the barotropic model, going back to the days of punch cards. Now it to me, I mean, it's evolved pretty rapidly. If you, and this whole like American, the GFS versus the Euro, which always gets, you know, talked about in the news. Historically, it's only been the international Met centers that run global models, and they, you know, most of them, and some of them still today, used to be run on spectral resolution, which is different than like a global grid. But you're looking at the entire Earth, which is very different from your limited area models like MM5 and WRF or RAP and HER or whatever, which are just a subsection of the Earth. And you have a global set of observations, you initialize that and project forward. Most of these go out, you know, a week or two. And, you know, I'll let Alicia talk about the evolution of the verification scores and why they chose what metrics they decided to choose to verify these. But it has historically been a government funded effort because you needed massively expensive supercomputers to do all the number crunching. And it's only been in the last probably 5 or 10 years that the code has gotten efficient enough and the cost of compute has come down enough to where private industry and universities can run these at a reasonable cost. And even at a relatively low resolution, you can now run the global model on your laptop. But that's, you know, that's kind of an interesting, completely different sidebar conversation. But there's always been kind of a friendly competition between the international Met centers about, you know, who's got the best skill scores. And, you know, we should talk about whether, you know, all the inside, is it really friendly? It totally is. I've actually spent a lot of time over at the UK Met office in ECMWF working on data assimilation and observation errors and stuff like that. And a lot of their scientists have spent time over here. We're constantly sharing stuff back and forth. But it's still a friendly competition, and that's what keeps it interesting. It's also really nice that we all, like the international community, has different models with different DA techniques and physics and stuff, because when the forecaster's actually doing the forecast, they're looking at a lot of different models. They're looking at the model consensus. They're looking at all these different ensembles from the international centers and what's the spread on those. And there's a lot of information that goes into this. And if the world was only using one single model in deterministic mode, the forecast would be awful. So anyway, I'm gonna hand it over to Alicia to talk a little bit about the history of the evolution of the scoring.
Oh, yeah. Thank you, Neil. I don't know if people can see me. The green box always stays on you when I talk, but I think, you know, it's important to know what we use for scoring and why we use it. And I think that we're using this thing called 500 hectopascal, so like middle atmosphere, northern hemisphere anomaly correlation scores. Like, that's what we use. And I think we used that for as long as we did because it was something that we could measure, because it's what's called a grid to grid verification. So we had like a global grid of like what we thought the truth was and a global grid of the forecast, and we could compare the two. And it's also one of our longest standing metrics that we had. So I practiced this. Can I share my screen really quick? I'm going to try. We're going to figure this out. Can you see this? Hopefully you can see this. So this is from 1984, which is older than me, to 2021, the global model anomaly correlation scores for the Northern Hemisphere at day 5, specifically at day 5. And what you can tell over time is that the lines are going up from left to right, which is a higher score, which means improvement. And initially in like the 80s, the line is fairly steep. I mean, there's significant improvement over time with these lines. And then you get to like the last 10 years and it levels off. It levels off completely because we're hitting, you know, this point of we can't actually improve too much more. Like we're getting to the edge of like chaotic theory, you know, predictability. And but the great thing is, you'll notice for the last in 2021 here, is that 4 global models, us, that's the GFS when I say us, GFS, ECMWF, Canadian, and the Met Office are all above 0.9 in the annual mean. And that's incredible. I mean, we all benefit from that. It's like Neil was saying, like it's friendly competition and it's fun to talk about like a sports team, you know, like go Bills, but it's not like, it's more important that we're all good, because then things like the national blend of models and like things that take all the models together do better if we all do better. So just wanted to share that briefly here, and I'll stop sharing my screen.
Thank you, Alicia. And as we transition back here, one of our, this might be the biggest challenge of this hour. One of our questions coming in is, you know, can you define all acronyms that you use? So we've used ECMWF, which produces what is commonly referred to as the Euro model. So if you see that on TV, the Euro model, that's coming from the European Center for Medium Range Weather Forecasts. And you may hear of UK Met. So the United Kingdom has a sort of national weather service, but it's called the Meteorological Office, the UK Met Office, often just shortened to the Met Office. That refers to the UK. And then there are, you know, various other countries that have, you know, agencies similar in nature. So just wanted to throw that out. Awesome. You know, I think that's a great point, Alicia, with the, you know, the law of diminishing returns, that at some point, you know, how much more skill are going to be able to squeeze out of the models. Kind of switching gears, but not really. Again, kind of looking at the GFS and the Euro. Neil, it's not an apples to apples comparison. The ECMWF is laser focused on their global deterministic and ensembles. And maybe this is better for both of you, but NCEP, the National Centers for Environmental Prediction, has an incredible broad scope of models. Could you just kind of throw, you know, we have wave models, we have,
so that, you know, you're spot on. So it's often that the Weather Service is compared to the European Center, but that's not apples to apples from a variety of reasons. So starting at a really high level, the Weather Service's mission encompasses all sorts of stuff, you know, like you were saying, from everything from like harmful algal blooms to space weather to short-term high-resolution convection to long-range climate dynamic models. The European Center only cares about the medium range forecasts, like 5 to 10 days. That's all they care about. They run a deterministic model and an ensemble, and that's it. And if you look at the production suite at NCEP, they have to manage all of these models. And historically, all these models had different code bases, different libraries, all these different dependencies. And so one of the things that I'm working on with the unified forecast system is to try to consolidate as much as that as possible, and then also make it community friendly, so it's not just unique to the compute hardware that NCEP has. but that, that on like a management mission level are the major differences. On a GFS to Euro, they're still different. So one of the big things the Euros claim to fame is they actually use true four-dimensional variational assimilation. And at some point in the future, I think with the transition over to the joint effort for data integration, the JEDI program, there is a 4D VAR option in there, but more importantly is what I'd refer to as the observation binning window. And that's whenever you initialize your forecast, you call that time, say, t equals 0. You have this span around that where you pull in all of these observations to build your best guess of the current state of the atmosphere. And the European Center's observation binning window is bigger than the GFS, and it extends further out into the future. So if you're comparing the 12Z Euro to the 12Z GFS, the 12Z Euro actually pulls in more data before it cuts off and starts its run than the GFS. So it's already starting with more information than the GFS. But this is, the trade-off is this is why you get the GFS before the Euro, So, I'm told that the reason why these wall clock times originated was because the news media wanted their GFS output before they went live on air, but it's not my gig, so I don't know. But, if you're already starting, even if you compare 6Z to 6Z or 12Z to 12Z, it's not apples to apples.
No, great. And, we're getting a flurry of questions here, and some we'll get to at the end, but two kind of jump out at me. One is, what impact has climate change had on model accuracy? And I guess I'll preface that by saying, we're not talking, decades, how that will impact model accuracy. But between both of you and sort of the verification, Alicia, and just sort of generally, Neil, how have the models improved? And I know they have, with sort of identifying these extreme weather events, the precipitation forecast for like Hurricane Harvey, just even above the legend or the scale on our graphics.
So a lot of those are, it's always the outline event. So this is one thing, and we could go down the AI rabbit hole of tuning to the mean, but while you could tune everything to the mean, and so maybe this is a MOS or diecast or something too, it's really the outline events that are problematic from a forecaster's perspective. I mean, if the average weather was the mean, then we could all just look at the Farmer's Almanac and go home. So that presents its own set of challenges, because when you're doing a lot of verification, you're looking at months to years worth of reforecasts and tests, but you're also doing case studies for extreme events to see how the models handle those. As far as the impact of climate change, that type of information is, that's probably a couple orders of magnitude in threshold below what we tune a lot of the models for. But I can see a situation where when you're doing like statistics of generating your background and things like that, there's a lot of climatological information. So if while it's great to have a really long span of time, you also dilute the near term average by including really historical trends going further back. So even a really, really short range version of where I would see this crop up in these models is back when GFS used to use a 30-day climatological mean for sea surface temperature versus as recent assimilation of SST data as you could. A lot of those transient features in the sea surface currents were washed out by the mean. So I would expect it to evolve over time, but the ability to forecast the growing number of extreme events is less based in background climatology and more based on really understanding the physics.
So Alicia, I got a question here for you. Someone
Right.
has asked, which are the best models to use for winter weather, tropical weather, severe weather? And I guess, what makes this question so interesting is a lot of verification of models. It's like, 500 millibar heights, which is not sensible weather. And we're not, we don't live halfway up into the atmosphere. Do you want to say something about, how the different models, they have their strengths, they have their weaknesses, they have their biases. It seemed to me this past winter that the GFS was kind of, nailing some of these bigger snow events, especially here in the Northeast. What are your thoughts on that?
I think what I'm going to say about that is attack a certain part of what you said, and that's the sensible weather part of it. I think that if you only look at 500 hectopascal anomaly correlation AC scores, that it only tells you part of the story. And I think that we need to focus on things that affect people on the ground. So like you called it, who don't know what we mean when we say sensible weather, that's like temperature at 2 meters. That's like, I'm not 2 meters tall, but like that idea, like where we stand. Precipitation, things that you can like feel, wind, like they're very important. So all these models, like you said, and I won't get into specific, I'm sure the person wanted specifics, but that's a whole other seminar, is, models have things they're very good at. Like, for example, Neil was just telling me recently that the GFS does very well at wind speed at the height of wind turbines, so in certain scenarios, it's excellent for that. This past Atlantic hurricane season, the GFS had the best track forecasts of any global model in the medium range, but like, that isn't true every year, that kind of thing. It's important, I would say, for forecasters to know and learn the model biases. So if they see a certain situation, they can be like the AI and go pattern recognition and be like, in this situation, I know that the Met Office rocks, so I'm going to, weigh that more in my forecast for this particular thing. So it's more, forecasters should try and learn it on their own. And a plug quickly for the EMC model evaluation group. We try and provide this information to forecasters to let people know, like, this is a known bias of this model. Like, this model will underpredict intense rainfall in this area, just like as an example, something like that. So we can try and tell it to you. So please seek us out as a reference for that. But also, I think forecasters do a great job of becoming their own reference just by looking at the models over time.
That's a great point. And this is where the human in the loop is really important, because, we've already established that it's not good to just have one single model. We got to have a full suite of models, but then we got to know as forecasters when to use which ones. And I can tell you, from living in the Carolinas, I have been completely made fun of by people who live in other states for relying on the NAM 3K for precip type events, but it's one of the only models that does a really good job at resolving the cold air damming and the warm nose. And every time every model calls for snow, and believe me, I wish those models were right, I'm pulling for snow too, it always ends up being freezing rain at my house.
So Neil, you kind of answered partially the question I was going to ask, and Bruce has a great sort of question comment about, the higher resolution models are able to, give you guidance on, terrain induced weather and more, regional and local impacts. So let's say, let's put Neil in the forecaster chair. All right. You have all the models, whether it's American, European, whatever. Let's walk through a nor'easter, and it's, I don't know, 5-6 days out. People are already on social media blasting out their snow total maps. It's going to be Snowmageddon again. What models are you looking at? Ensembles first? Are you then going, staying global? Do you go, toward the NAM at what kind of day period? And then are you going back to, a global model, kind of lay it all out? And then when, then you got the HER, which is, Another
All
story,
right,
for
so
another seminar.
let me preface this by I'm a modeler. I'm not a forecaster, so this is not career advice if you want to get into forecasting, because I shouldn't be trusted. But here's what I normally do. First, I'll start looking at the global models. I'll look at the GFS and the Euro and anything else I can get my hands on, Canadian. And I'll look at the deterministic runs first. And of course, there's always wild anomalies and crazy storms, especially the further you go out. But what I'll do is I'll flip between runs. So if one of the telling things is if a storm's like, it's 976 low right off of Cape Hatteras, and then you go to the previous model run and it's not even there, I got pretty low confidence. But once I start seeing a storm show up repeatedly in different places, but kind of the same pattern, then I'm like, all right, something's going to happen. And then I'll start checking the ensembles to see what's sort of the spread. Are the ensembles tightly clustered around something similar to what the deterministic has? If the spread's all over the place, then I'm back to no confidence world where I just sit around and wait for the next run to see if anything changes. And eventually, as the runs come in, the successive runs, and the event is becoming closer and closer in time, you'll usually see the deterministic jumping around less and less. You'll see the ensembles starting to tighten up. And then I start to look at things like, does it physically make sense? For example, with the nor'easter situation, is the surface low forming where I would think it would? What is the sea surface temperature? Is there like a warm core eddy or Gulf Stream backed up way against the coast? Where's the frontal boundary setting up? Is the upper level trough too west? Is it too detached? Is it right over it where it's not going to be tilted enough so that there's really good phasing? And then, once that event gets into sort of the NAM range, like the 72 to 84 hour range, then I'll start throwing that one into the mix. And then I'll start going to buff kit. And, shout out to the people who still maintain buff kit warehouse website. But I'll start looking at that. I'll go to tropical tidbits. So shout out to Levi. And click on and pull up SKU-Ts to make sure that the SKU-Ts make sense with if it's producing whatever precip type the forecast is. So I'll start comparing SKU-Ts to what the model's outputting for snow and wind and everything else. And then inevitably what happens with these nor'easters is I somehow end up in the short term looking very disappointed at the NAM because it does a great job of resolving the warm nose, which just means that I'm going to be disappointed and not get any snow, but it's all going to be freezing rain. In which case, instead of pulling out the sled, I'm pulling out the generator and worried about losing power from ice. So that's kind of my 2 weeks of getting ready for the nor'easter when it shows up in the models in the winter. But not sure if I answered your question, but I did. This made me actually think about the GFS snow total issue, and maybe Alicia, you wanted to talk a little bit about this on some of what was going on with the land surface model and the snow totals.
Right. Yeah, for sure. So people may be aware that this last February, a very large, very mixed precipitation storm spanned the US. This is extreme. First week of February, it was like Texas Panhandle through Maine for mixed P-type. And what was happening was people were starting to notice in the forecast, and this is people at EMC where I work, which is the Environmental Modeling Center, regular people who are, just interested in forecasting, and then, professor, like fill in the blank, we're noticing these extremely high snowfall totals in places that was not the primary precipitation type. Like that was not what was supposed to be happening. So what we did in the model evaluation group and at EMC was we all dug into the physical GFS code. And unlike the NAM, which had started to be really specific about like, freezing rain has a very different density to it and piles up differently than snow does, and all of these things were corrected, fixed in the NAM. The GFS, when it switched microphysics, And microphysics is, what helps you with the different precipitation types and things like that. When it's last time it switched it, the code hadn't been updated. So what was happening was in the land surface model, all of these different precipitation types were falling and hitting the ground, and like frozen other types like snow, but also graupel, and also this thing called cloud ice. And freezing rain actually isn't a frozen precipitation type. It's liquid and it freezes when it hits the ground. But all of these things were being tallied as snow at the time. And that's why these crazy high totals were happening. And I think it's understandable for people to ask, like, well, why wasn't that seen before? But I would say that talk about an outlier event, that mixed precipitation event, the geographical area, the span of time that it was, you had people across 2/3 of the country identify, in their area, like this issue was happening. And so we've seen it now. It will be added, it will be fixed in GFS, the next installation of the GFS, which is a minor upgrade, and that's in the fall and early winter of this year. Another thing that's going to help, because that isn't the only thing that was going on, is we're going to switch the microphysics schemes for the next version of the GFS, like the next big upgrade, which is in early 2024. And that will switch the microphysics schemes to one that doesn't produce as much erroneous cloud ice and things like that. So we're getting better. And again, thank you to everyone who looks at these forecasts, because during the period that we evaluated it, we didn't have anything like that event, nothing to compare it to. And then when we had it, it's so obvious, but without that event, we didn't. So yeah, thanks for asking, Neil. I'm happy to report that will be improved considerably prior to this winter. So that'll help a lot.
That, what you just discussed is a perfect case example of why we need community modeling and the community's involvement in this. Because, I mean, to be honest, I don't plot a lot of those variables that people were seeing, and I wasn't seeing that stuff. I was looking at other variables. And so it's interesting to see when the community identifies this stuff. And I would love to see in the future the community, particularly PIs at universities and their grad students and postdocs or whatever, actually tinkering around with the code and coming up with ideas on their own and contributing them back through the EPIC process.
So I'll jump in here, and this hour is flying by, and we do want to get to some of the questions here. And again, one of our challenges here is that we have, I see we have Lance Bozart joining the webinar, which is awesome. But we also have people who may even be struggling understanding terms like ensemble, which was more of a foreign term to even professionals 20 years ago. And so we have a lot of different ranges of understanding of what we're talking about. We even have a question on quantum computing and how weather models are going to evolve in the future, which I'll certainly pass off to someone else. But ensembles, and I'll try to explain it in fundamental terms, but maybe one of you can dive a little bit deeper. So the way I understand ensembles is you can create an ensemble out of anything, right? You can have, you could pull a European and a GFS and a Canadian, and that could be your 3-member ensemble. You could run the same model with different observation parameters. You could run the same model with different physics parameters. And as long as you have enough computing capacity, the computer's the limit on how many members or individual runs of a model, how many members are in your ensemble. And the idea, I think, is if you have, if you're capturing all the possibilities, right? If your upper air winds are observed incorrectly, maybe they're 10 knots off, but if you have that incorporated into your ensemble, that solution may capture that observation inaccuracy or a lack of data. Am I getting it, Neil? I mean, you're nodding a little bit.
Yeah, an ensemble is just a set of predictions. Really, I mean, you could use different models. You could use a time lag ensemble, which is the same model but initialized at different times. I mean, typically what happens is we take a model that's configured the same way, and we perturb the initial conditions and try to get a decent spread before we initialize it. And that goes back to what I was referring to earlier, is this observation error and representativeness error and uncertainty. So let's say, for example, you launch a weather balloon and its air and temperature at some height is plus or minus 1 degree Celsius, right? Well, so you know it came up with a number, and you're pretty confident that it could either be plus or minus a degree on either side of that number. So then what you could do is you could run an ensemble, that a 3-member ensemble that is this number and plus this number and minus this number, and that covers the spread. So that's kind of a extremely idealized situation of trying to mathematically account for the uncertainty that you know is inherent in the system. And when you project that out into the future, it's interesting because when you project that out into the future, if you get a wildly diverse set of answers back, then you know that your initial conditions, whatever they are highly sensitive to whatever's going on in the atmosphere. If you get a very tightly clustered result back, then you can basically have a lot of confidence as a forecaster to say, okay, we know these observations aren't right and they're all approximations at the start, but no matter how differently we observe the atmosphere, we always get the same answer. It gives the forecaster a lot more confidence in what they're going to write down when they predict what the weather's going to be.
Great. All right. Well, we still have a lot of questions. One we've kind of touched on, but maybe not specifically, which is, do certain models perform better in certain parts of the globe? I mean, the media, we're obviously focused on the Northeast, and some models capture the formation of a nor'easter better than others, or they have their biases, all of that. But and obviously it's also very dependent on where your observations are coming from. We're not as good in the middle of the ocean as we are over land. But anything notable that either one of you want to say about that?
I'm gonna let Alicia answer that first, and then I'm gonna follow up with a really funny story.
Yeah, no, thank you. I'll tackle that one. So I think it's actually super important what you said about like different areas of the world, and subsetting, meaning like breaking up verification to look at pieces. Because if you look at like the Northern Hemisphere as a whole, it's going to give you this big whole Northern Hemisphere average, but it doesn't tell you about what a model does over, say, a particular land surface type. Like maybe your model does terrible over the corn in Iowa when the corn is fully grown. Like maybe so it's important to subset your verification to look at over this extremely arid region, this global model seems to be way too warm, say, over the arid region, but over a forested region, that isn't true at all. So then you can start identifying where your issues are. If you can start looking at specific areas and being like, what's specific about this area? What's specific about this area? And then look into it and say like, oh, our coupling with the land and the soil state over the desert isn't good. That's not true, but that's just an example. But yeah, it's very important to understand that models do behave differently over different areas. And the new EMC Environmental Modeling Center webpage, verification webpage, does subset specifically. And we're actually switching to new subsetting the next time we upgrade it to look at the land type, not just region. Don't just say the Northern Plains, talk about the land type, and pick it apart a little more.
Oh, very interesting point there.
So let me, I'll tell you a funny story. It is related to region, but it's also related to time horizon. So I was involved in a data denial experiment many years ago, looking at high resolution vertical profiles from aircraft data, but it was just US domestic fleets. And we were using the RUC model and seeing a positive impact, as you would expect, in a short-term model run in the same domain that these planes were flying. But then we gave the data to the European Center. And they're like, we don't see any positive impact until about day 5. And then we actually see a little blip from like day 5 to 8, which, you know, when you think about it, makes a lot of sense, right? And so then I started thinking, you know, if we're struggling with doing emergency like 6 and 18Z radiosonde launches when there's an impending landfalling hurricane and we can't quite get the track right, why do just Florida? Why not do like Alaska? I mean, if you're worried about what the track's going to do in like the 3 to 5 day range, you got to go further west, because that's where the air is that's going to be influencing things that many days later as it moves east. And so it was interesting to me to think, well, you really want to improve the skill scores over the US at, say, you know, 5 to 10 day, you really need to start thinking about how well you observe the Western Pacific and Asia. And if you really want to go out a week or two, or even down into the tropics, if you trace back some of these airs, it's lack of observations. I mean, Africa is a massive data void when it comes to looking at data sparse regions for initial conditions. And this is something the WMO, the World Meteorological Organization, is aware of and trying to tackle. But if you think the US has challenges with deploying observing systems, imagine what it's like in some of these other countries, these lesser developed countries that don't have nearly the means or the budget to do it like we do in the US.
No, this is all good stuff. Gosh, we have about 13 minutes. I would be remiss. Keith or Gideon, any questions bubble up on your radar screen here? And when Neil, every time Neil mentions observations, you know, we all know that observations lead the way, as I also see Fred Carr on as an attendee. Keith or Gideon, what do we got?
Keith, I yield to you.
I do see a question.
I think I was just going to jump in here and just say, you know, one of the questions that came up was talking about whether machine learning was going to play a major role in weather forecasting. And I know there's lots of work that's been done on that. And Neil, I've heard you talk about this in the past. I think that would be a great question for you to field.
So I'm going to go to like my limits of predictability, as I know the extent of reality in my brain, and then I'm going to go past that into the realm of science fiction. So where I think things are going into the future with the trend, and this isn't quite quantum computing, because the NWP community is a couple processors behind that. We're still figuring out GPUs, but I think you're going to see the age of deterministic forecasting go away. And I expect that you'll see nothing but high resolution physics resolving ensembles. And you won't, the only reason why we run a low res ensemble with a high res deterministic is because we just don't have enough compute to run a high res ensemble. It'd be great if we did. But let's take that one step further. There's been a lot of hype in the press about artificial intelligence being able to predict the weather. But one of the things, if you read the fine print, is all AI and machine learning needs some sort of training information to learn from. And all these AI systems out there that claim to predict the weather, and they can actually do a pretty good job of predicting it, need a very high resolution, accurate reanalysis of history. And you're not going to get away from building a reanalysis without observations, data assimilation, and a physics-based model. So I can see a world in which AI would be used in a prognostic way, because it would be really cool if I could run my high-res ensemble in like reanalysis mode, and I didn't have to worry about making sure I got my run finished by any certain time, so I could build a lengthy historical reanalysis at a super high res, and then train my AI systems to just worry about predicting the future every few minutes to crank out a forecast. The other thing that makes me a little bit nervous, and I don't fully understand a lot of how these deep neural networks train themselves, is again, this goes back to the fact that the forecasters are worried about the outline events, and the sheer mathematics of training something over a period of time tunes it to the mean. And where I would really be interested and concerned about how well it performed is not the mean. I don't care if your forecast can predict the mean. I want to know if your AI forecast can predict these extreme outline events, because those are the ones that impact people's lives.
Yeah, thank you, Neil. This may be for Alicia, maybe Neil, and Neil, I know sub-seasonal and seasonal prediction. It's been a priority, I think, for a handful of administrations, and obvious ties to the agricultural sector. We did have a question on seasonal forecasting and sort of like, is that the new frontier, or where we can get the most gains, Alicia, in talking about, what are we squeezing out of these models?
I think there's two frontiers, and I don't know if the second one will surprise people or not, but it might. So the first is seasonal forecasting. I mean, it's been the frontier for a minute now, and I think that there's huge things to be gained from talking about using AI, for sub-seasonal and seasonal forecasting, because you can save lives and property and help the commerce of the United States if you can predict out to week 3-4. That means 3-4 weeks from now, where it's going to flood. I mean, you can, or let's say something else. Let's say heat. Gas companies can transition where they're selling, their natural gas. Like it's a huge market in seasonal and sub-seasonal, and the models can only get better from here. So I think that's way of the future. And second is fire weather. I think that fire weather is going to be and is becoming such an important thing to get right in the United States. And I know that we're working toward that now. Like there's starting to be positions that are like fire weather specific. And I've even heard talk, I don't know if it'll ever happen, of like a fire weather NCEP center, because right now that's part of SPC. And I think that fire weather and seasonal forecasting and models that do that well, like smoke prediction, even, that air quality and stuff, it's those two, I think, are the low hanging fruit right now and are critical to us continuing to do the mission of NOAA. So, which is to save lives and property.
Great points. Neil.
Yeah, I would say I completely agree with Alicia. I think that there's a huge opportunity for AI in the longer range seasonal outlooks, because it's a lot more pattern recognition based than physics based. And you can have, like your AMO and MGO and PDO and all these things. A lot of those are relatively stable signals that are more easily predictable. And so that lends itself better to AI. Fire weather has its own complete different set of challenges. And to me, that's fascinating, because you're really getting into the land surface model coupling and soil moisture. And then you get these fires that generate their own weather, really. I mean, if you think an asphalt parking lot heats up, imagine what an entire, hillside of burning pine trees can do. I mean, this is how they generate their own wind currents and everything else. And, subsequent evacuation orders, and then your firefighters making sure they deploy in the right place. But it's not just based on the current wind, but what could the wind change with the fire? I mean, that's just the idea that we're thinking about trying to figure out how to predict that, to me, is pretty amazing.
So with the couple of minutes that we have left to the top of the hour, and Neil, I do want to give you some time to talk EPIC, the Earth Prediction Innovation Center, and the Unified Forecast System. We'll kind of end on that note. But for both of you, what's your wish list for the future? Whether it's observations, data assimilation, whether it's computing power, like if you had 3 things that at the snap of a finger you could have that will help drive the model performance to new heights, what would they be?
Neil, can I go first and then you can?
Yeah, I need some time to think
I'll-
about this.
First would be more compute for me. I mean, this is keep in mind, I'm at the model about I'm the environmental modeling center, but more compute, more bandwidth to get the forecast out, because a forecast that is perfect that you can't disseminate is not helpful. And 3 would be the people to do it, to do the jobs. And that, you put us on the spot, but that's literally it. Compute, bandwidth, bodies, to get the people to do the job. But yeah, that's what I would do.
Yeah, I'll second your compute. And I mean, maybe I'll sort of maybe I'll do like a 2-for-1 on compute and talk about code efficiency and consistency and scalability, which does remind me of some language challenges with coding languages, which really takes me to my number 1 wish, is that the NWP and atmospheric sciences becomes a greater focus in the middle school and high school age group, because I would really like to see younger students driven in at the undergraduate level who are interested in the math and the physics. I get it that a lot of people are interested in weather. They want to be a weather forecaster because they see their forecaster on TV. I came into weather from a physics background by accident, basically. And I would like to see more interest and exposure at the younger and younger levels, because if there is a deficiency I see in the entire system, it's that the universities aren't producing the future brain trust that we're going to need to solve a lot of these problems. And I think probably, tying into that, my third one would be understanding of the uncertainty of weather prediction and the models in the general community, and the understanding of risk tolerance. That's a big challenge, because the risk aversion in the weather forecasting community stems from the fact that everyone gets upset and complains when you get the forecast right, but no one gets a pat on the back or a kudos if they nail the forecast. And that negative feedback is a disincentive to innovation, and it's a challenge.
Lots to think about tonight for sure. So thank you both. And I again, Neil, I do want to hand it off to you sort of for the last word there. But Alicia, awesome perspectives. Thank you so much for joining us. And for those who are clamoring for more of this discussion, I'm going to try to strong arm Neil and Alicia maybe for a part 2 later here in 2022. But Neil, finish us off here with sort of your thoughts, where we're going, on EPIC, on UFS, and then we'll say goodnight.
So this is a huge paradigm shift for NOAA. Historically, the models have been hard-coded to run only on NOAA's compute architecture, which is very different than the compute architecture that universities and industry have access to. And so if you don't have a security clearance, you can't log on to NOAA's machines. That's one issue. And so historically, you couldn't run the code except on NOAA's machines, which meant that NOAA had a big challenge of accessing the expertise at the universities and at innovative private companies. So what the UFS does simultaneously is it consolidates the production suite into a common code base, but also refactors it with the help of EPIC to make it largely hardware agnostic, and in an ideal world run on any kind of compute architecture, whether it was Google or Amazon or Microsoft Cloud or your laptop. I mean, I've run the UFS on a Raspberry Pi connected to an iPad, and there's a lot of benefits to that. The first one is just general outreach. You're crowdsourcing model development, which you would think generating the Wild West of model development by throwing your code out there would create a lot of challenges, and it does. And one of the points of EPIC is to filter all those crowdsourced innovations, because a lot of them may work, some of them may not, some of them may fix one thing but break something else. there's a lot of testing and refinement, but in general, if you just put all the stuff out there, you're going to get some really wild, crazy ideas that come back that could be game changers that we just haven't thought about because we're just so focused on what we do every day. The other thing is, if you have the ability to run a lot of this code on, say, laptops, it becomes a completely different teaching instrument in the classroom for teaching numerical weather prediction. You want to be able to teach what it's like to run a model. You don't need a supercomputer. We can talk about doing data assimilation or NWP with idealized cases and toy models right in front of you in the classroom, and it'll run in a few minutes while you watch it. So I did want to plug a couple things. So if you look up Epic, there is a workshop coming up. It might be full already, but there'll be subsequent workshops. The first one is June 6th. It is just a couple hours, and you will be trained on how to run the short range weather app in Amazon Cloud. And then also the UFS Epic Summer Workshop. It's July 18th through 22nd, I believe. If you Google UFS or Epic, it's listed on their website. There we will be discussing the future developments of the modeling program, the governance of the community model, because this is really a modeling development effort for the community, by the community. So we need everyone's input and involvement if you really want to see the American model back on top.
Great final words there, Neil. And for those who have submitted questions and we just haven't been able to get to, I think we are able to capture them, and we'll make every effort to in some way get those answers back to you. But regardless, thank you again. Thank you, Alicia and Neil and the AMS staff. Quite a conversation over the last hour. And, who knows, maybe we'll get you back. So thank you. Thank you, everybody.